Hello all, welcome to the video lecture. This is Ramesh Lama. Today we will be discussing about the sharpening spatial filters. In last class we discussed about the smoothing filter and the sharpening filter is just opposite of that. So the principal objective of sharpening is to highlight transitions in intensity. The sharpening filters are based on computing spatial derivatives of an image. So fundamentally the strength of the response of derivative operator is proportional to the degree of intensity discontinuity of the image at the point at which the operator is applied. So the derivative of a digital function are defined in terms of differences. Although there are various ways to define these differences, we require that any definition we use for a first derivative. Here the first derivative of any function fx is defined here as df by dx is equal to fx minus 1, which is equal to f dash x. It's the backward difference, means we take the difference between the current pixel or current position with the preceding one. And in forward difference, what we do is we take difference between the current pixel fx and the preceding one the succeeding one fx plus 1, which is also written as f dash x. And in the central difference we take the difference between the succeeding one and the preceding one. It's also written as f dash x. And while using it in image signals or images, the first derivative must be 0 in areas of constant intensity, and it must be non-zero at the onset of an intensity step or ramp, and must be non-zero along the ramps. And the first order derivative of 1D function is a difference, as we have discussed in just before. Del f divided by del x is equal to fx plus 1 minus fx. Let's see an example. Here we have a signal fx, and when we take the difference, when we take the first derivative, we just take the difference between the current pixel and the succeeding one. And at the first position we just take the difference of itself, and when we take with the with second, then we can get this we can get this result. Here we get 10 minus 10 is equal to 0, and 10 minus 15 minus 10 5, and 10 minus 15 minus 5, 10 minus 10 0, 25 minus 10 15, 20 minus 25 minus 5, 20 minus 20 0, 20 minus 20 0. And here we take the difference of itself at the beginning and at the end of the beginning and end pixels are subtracted by itself. And this is for the second order derivative. We will discuss in later. And for the backward difference we use the mask, this minus 1 and 1. In forward difference we use this mask, and for central difference we use this mask. And these marks, as we have discussed in our last class, we just multiply the pixel with these marks and take the sum of those we take the sum of product. And the second derivative or second order derivative, it must be 0 in constant areas, and it must be non-zero at the onset of and end of the intensity or step or ramp, and must be 0 along the ramps of constant slope. And the second order derivative of 1D function, we write this as it is the derivative of first derivative, so it can be written as fx plus 1 plus fx minus 1 minus twice fx. We take the derivative of the first derivative. So when we see the example, let us see we have got the image here. This is our image, and we take a signal at the specific point, this white dot area, and when we take the 1D signal, and it looks like this like the right on the right side we can see a image of line. And now when we see the gray level profile, it looks like this, like from 0 to 7, it varies from 0 to 7. And and if we look at the image strip, and this gives us the pixel value or pixel intensity value. And when we take the first derivative, and here we get the first derivative of this image strip and second derivative of this image strip. And while looking at the first derivative, at the ramp we get some positive value, and when it has a smooth area or constant intensity area, then it becomes 0. And when we go to the isolated point or at the peak, here again we get some value here. And at the thin line flat segment or at the flat areas, we get the derivative to be 0. And similarly, when we get at thin line flat segment, we get the value, we get some value, and at step we get some value, and here in flat areas or in smooth area we get the derivative to be 0. Similarly, in case of second derivative at the ramp area, we have just discussed before, the second derivative becomes 0. However, at the isolated point or where the intensity value changes, we get some values here. And when there is the again here when the intensity value changes from smooth to peak, here also we get some value. And at the constant area it becomes 0. At constant area it becomes 0, and at the step area what we get is we get some non-zero value. At the constant slope or at the ramp, at the constant, here we get at this step we get some non-zero values here, and here also at this step point we get the non-zero value. We can see here, if we look at this, is the same that is illustrated more here, and this is for the intensity value. And here, like here we have got the first derivative and second derivative, and we get some non-zero values at this where the intensity transition takes place, and here as well where the intensity transition takes place. And this is the intensity and the first derivative and second derivative values. And here what we observe is that the first order derivative generally produce thicker edges in an image, and second order derivative give stronger responses to the file details such as thin lines and isolated points, and first order derivative have stronger response to the gray level step, and second order derivative produces a double response at the step edges, and second order derivative are better suited for the image enhancement. So we use the second order derivative for image sharpening, and that we call the Laplacian. And since we are interested in the isotropic filters whose response is independent of direction of the discontinuities in image to which the filter is applied, So in other words, the isotropic filters are rotation invariant. So Laplacian is the simplest isotropic derivative operator, and it's defined as it is the second order derivative. So to express in discrete form, here in x direction it is defined as del square f divided del x square is equal to fx plus 1y plus fx minus 1y minus twice fxy. Similarly, in y direction, it is the fxy plus 1 plus fxy minus 1 minus twice fxy, and when combined together we get this expression fx plus 1y plus fx minus 1y plus fxy plus 1 plus fxy minus 1 y minus 1 minus 4 fxy. And the filter marks here, we have got the two filter marks. These are used to implement the digital Laplacian, and marks B is used to implement an extension of this equation that includes diagonal neighbors. And the third one is C and D, two other implementation of Laplacian. These are also the implementation of Laplacian. One is the general basic Laplacian, another one is the enhanced one. So if the background feature need to be recovered but still preserving the sharpening effect of the Laplacian, then the basic way to use the Laplacian for image sharpening is like we take the Laplacian and we just get the we subtract the Laplacian from the original image if the center coefficient of Laplacian marks is negative, and if we take the center coefficient of the Laplacian marks as a positive, then we add, here is the center mask, and here we have got two Laplacians, one with the central with positive central marks and one with the negative central marks. And in order to preserve, we use this equation for the Laplacian filter, and if we simplify it, it's just once we simplify we get this equation. The final equation is 5 we multiply the original our central pixel with 5 and minus fx plus 1y fx minus 1y plus fxy plus 1 and fxy minus 1. And this is the example. Here is the blurred image of north pole of the moon, and we do the Laplacian, and we get the Laplacian with the scaling. This is one with the scaling, and the image sharpened using the mask in this is the these are the image sharpened. This one is the Laplacian, this one is the blurred image, and after we take the Laplacian we sharpen this image. These are the image that is sharpened using the above equation that we have just discussed before here, and these are the masks that we have used. And this is the composite Laplacian masks, and there are two composite masks and scanning of electron microscopy image. And here what we get is the results of filtering with mask A and B respectively, and these are the filtered image with mask. And another one is the unsharp masking and high boost filtering. This is a process commonly used by printing and publishing industry called unsharp masking, and it consists of the following steps. One is to blur the original image and subtract the blurred image from the original. The resulting difference is called the mask, and add the mask to the original image. What we have is unsharp masking. Subtract the blurred version of image by itself. Here we have got the fxy, its blurred version, and fxy the image, and f bar xy is the blurred image. and final gxy is what we get is the fxy plus the difference that g mask, and we multiply it by some scaling factor k, and we add this. And high boost filter, when k is greater than 1, then we call it the high boost, and choosing k less than 1 will de-emphasize the contribution of unsharp mask. So this is the original image. Here we can see here the original image, original signal, then the blurred signal, and we use the unsharp mask, and finally after adding it we get this, the sharpened signal. This is the sharpened signal because we add this part to the this original signal. And here is the unsharp masking with high boost filter, the original image, and result of blurring with the Gaussian filter, and we have unsharp mask, and result of using unsharp masking here, and result of using the high boost filter. We can see the difference between the only unsharp masking and the high boost filtering. Okay, this is all for the unsharp masks, and in our next lecture we will be discussing about the edge detection, which is also much more which also will cover this the topic we discussed here, the derivatives, and see you on that class. Thank you.